the cloud. I'm gonna hide my floating meeting controls. And I've already got Solidworks up and running. So hopefully this won't be too hard to follow along with. Starting off with this, we're going to cover topology studies or non-parametric design optimization, as well as parametric design optimization in class today. Because the non-parametric design optimization can take a long time to finish or to work, I actually came in before class and started running the simulation. It's running at about an iteration a minute, a little faster than that. You can see that it's on iteration 15 and it's on, so about every 30 seconds it's running an iteration. And it's going to keep going until it try to find the best case scenario where you have the lowest mass with a stress target of 20 megapascals, which will give me a factor of safety of 2 in this design, right? And we'll go ahead and we'll run this, and I'll have you guys run the same thing, but using a much coarser mesh, which will give you results, but they'll be bad results. And so we'll talk about kind of why that's bad. And then hopefully we'll still have time to go in and run a parametric design optimization using some of the results that we got from this non-parametric. And because I think the takeaway I want you guys to get from this is that the non-parametric modeling gives you results, but they're usually pretty kind of iffy. But it gives you a good idea of how you can shape your design to then run a parametric study to get a good actual design out of that, right? Sometimes you can get good results out of the non-parametric, but again, we'll talk about that when it comes out, and it'll be more obvious at that point. So follow along with me. Our goal today is to make a bridge. I just gotta minimize this before I can go to my other part 3. Oh, I just gotta be more patient, I guess. There we go. And we want to make a bridge that will span a 9-inch gap and fit within a 2-inch by 2-inch, kind of by 10-inch envelope. And I chose that size just so that way, for the idea that we can 3D print this and test them. And the next project for the 2 credit hour people in the course is to design that bridge and optimize it so it has the minimal 3D printing time using relatively standard settings. So using a 0.2 millimeter layer height, all of the default movement speed. So you can't go in to say, I'm just going to make it move twice as fast and make it super thick, right? So I have a really poor quality, but a bunch of material, and that's how I'll win. So kind of with the idea that you're using an appropriate set of settings for the printer, but trying to minimize the mass and the geometry to make that good. And then if you guys who are not in the 2 credit hour version of class want to do that just for funsies, we'll print out those bridges and we'll test them. Probably not next week, but maybe the week after. Have you guys submit those on maybe Thursday or Friday, 2 weeks out, or not quite 2 weeks out, so we can test them on Friday. Depends on how long they take to print. If they're going to take a long time to print and we have a whole bunch of submission, then we may have to push that back another week. If we only have the 2 people in the class who are doing the 2 credit hour version, we can probably test them on that Friday. All right, let's make it out. So I'm going to go to the front plane. I'm going to sketch on the front plane. I'm going to use a center point rectangle. And I'm going to just use this to define the envelope of my bridge. So I'm going to make it 10 inches long. I am in inch pound second. If you're not in inch pound second, just type in 10 inch and it'll convert to whatever, and then you can change your units afterwards. And 2 inches tall. I think on Canvas, I may have had 10 and 3, but then after running this a couple of times, I found that that's too big for a lot of these things to converge in any kind of reasonable time and give us even close to a good result. So I think the 10 and 2 by 2 will work better. So there's my 10 by 2 bar. I'm going to extrude that. I am going to use a mid-plane extrude. That's going to give me the symmetry about that origin. Oop, not 20, just 2, which is helpful for me from a general design standpoint. Again, just kind of good practice starting off. There's my bar right there. I'm going to set my material to ABS polycarbonate. Really, I'm not going to print this out of polycarbonate ABS, but this has a material strength profile that's pretty close to our PLA. It's got a yield strength of 40 megapascals, which is reasonable for what we have. You won't get that strength in the in kind of the layer by layer direction, the Z direction on the printer, but you'll get probably a little bit more than that in the X and Y directions. So it's not a bad approximation of the yield strength of the material. And so again, if you have a factor of safety of 2 in there, you'll be fine. Everyone able to follow along with that? Well, I know you're still waiting for Solidworks to load. All right, on this, I do want to have areas where I'm going to apply loads and fixtures. That's not just the entire face. So what I need to do is I need to split some of these faces to give myself areas to put those. So the way I'm going to do that is I'm going to go to the bottom of the part. I'm going to sketch on the bottom, and I'm going to draw 2 lines, both a 1/2 inch from the sides. And then after I finish doing those lines, I'll use those to split the faces of the part. So that way I have specific regions that I can apply loads to. I'm going to put both these lines, again, a 1/2 inch from the left and from the right. And then I'll exit that sketch. That's good for my bottom. I'm going to come to my top, do largely the same thing, except for I'm going to put my 2 lines a 1/2 inch apart in the middle of my part. I could probably use a center point rectangle for this too, but do 0.25 from the left, and then I'll do a 1/2 inch apart. I could also use constraints to add symmetry or whatever there, but this works fine and it's pretty quick. Do you have any questions on making those sketches? Pretty straightforward. All right, so the split face tool, it's actually not called, it's called the split line tool. Well, this really uses a line to split a face on a part. This is really part of, I think, you use a lot in like molds. So if you want to split a face, so you can add different drafts or something like that to different faces. Or if you want to use a section of a face and do a cut extrude or something like that. It has a lot of different uses outside this application, but also very useful when doing simulations if you want to isolate specific regions. To be clear, this do not have to be like across the entire body. You could have a circular face or any geometry you wanted. So if you had like a specific mandrel that's applying a force to a part and you wanted to just cut out the face of that mandrel to apply a load over that area, you could do that too. We're just using this because it's simple and we don't want to overcomplicate our simulation. So I'm going to go into that split line tool. Again, that's under this curved split line. Yeah, Will? It's a 1/2 inch from the left and the right for the bottom, and it's a 1/2 inch across centered on the top. I can show you guys that real quick. There's the top dimensions. There's the bottom dimensions. So I'm going to go to that split line tool. The curves I'm going to use are the sketches. So I'm going to use the sketch and then the bottom face. And I'm using the projection. The projection just projects the sketch onto the face. You might think you might want to use the intersection, but the intersection looks for the intersection of 2 planes, not a line and a plane. So you want to use this projection tool. And I'm going to change my render options so you can see that better. I'm going to remove the appearance of the polycarbonate. If you guys want to know how I remove the appearance of the polycarbonate, you want to do that yourself. You go to the model kind of options up here at the top. The ABS polycarbonate, whenever you apply a material to a part, it also will apply an associated appearance to it. You go over here to the display manager, which is using these little arrows at the top of the options. You can get a list of all the appearances that are applied to the part. And if you want to go back to the default appearance, I think you can just hide that, but I just deleted it because I don't really care about the appearance at this point. So I just clicked on it and hit the delete key. You can probably undo so you can see that. So there's the appearance here. So it is just to hide this. Yeah, I mean, that's the same as saying delete though. So there's probably a way you can hide it and not delete it so you can toggle it on and off, but I don't care right now, so I'm just going to delete it. And now you can see that I have these two faces right on the bottom that have been split out. I'll do the same thing for the top. So I'm going to go into curves and split line. I'm using the projection. The projection sketch is just my sketch 3. And then the sketch or the face I want to cut is this top face. And that gives me the setup that I want to be able to run this topology study. All right, I don't need you guys to follow along with this, but I want to show you. We're still running. We're on iteration 38. I can stop this before it's finished and see kind of whatever the results are currently at. But before I even ran the topology study, I did run a regular static simulation to check and see if my setup for the simulation was appropriate or not. Especially if you're going to be investing, an hour of computational time into running a study, you want to make sure the constraints that you have set up as far as the fixtures and the loads are appropriate for your part before you even run any topology study. So I almost always recommend you run a static simulation, find out what your loads are to start with, and then use that to kind of help inform your mesh size as well as kind of what your goals are, from the topology study. This one here, if I show you the stress distribution, we've got a maximum stress kind of just in these corners and around them, kind of around that 4 times 10 to the 5. So that's 0.4 megapascals, and our yield stress is 40. So we've got a factor of safety here of, not 100, but maybe 50 or 60, which means that there's going to be a lot of reduction in size of this for it to become a optimized part. And that's really kind of pushing the limits. If I wanted to be more intelligent about this, I probably would have went through and decreased the width of this part. The height is helpful, but the width is not really all that helpful from the design standpoint. Make it, maybe an inch wide or half an inch wide. But again, I'm trying to keep the criteria inside the project a little bit broader. Does that make sense to everybody? So I would probably want to bring that original factor of safety down using some parametric changes first, and then go into the non-parametric modeler, right? I guess we'll set this up and then we'll talk a little bit more about, what do I mean by parametric versus non-parametric? So I'm not sure that that's clear for everybody. All right, so let's figure out how to set up this parametric study. So go back to your part. Yeah, well, this one here, it's 10 by 2 by 2. It's 10 long, 2 wide, 2 tall. All right, let's go into simulation. If you don't have the simulation add-in, go to the add-ins tab and then click on Solidworks simulation. And you should see the tab for that at the top of your screen. If you click on the simulation tab, it does take a second for it to load. So if it's not there, click it, wait a few seconds, and then it should pop up, and then you can come in and set up the study. So we set this up just like we would a static study. I'm going to go to new study, and then I'm going to come down to topology study, and you can call it whatever you want, right? So I could say like bridge non-para. Doesn't really matter what you call it. It's just going to name the tab at the bottom based off of that. And for some designs, you might want to run multiple studies, right? To kind of figure that out. So I'm going to accept that to create the study. And you should see some fairly similar tools here. If you've used, I added that appearance again. I thought I had deleted that. If you've run simulations before, right? So I have fixtures, I have loads, and then I have a couple of new things you may have not have seen, the goals and constraints and the manufacturing controls. Let's go ahead and set up the fixtures and loads because that's something that's fairly familiar, so it should make sense. I'm going to set this up as a fixed pinned bridge. So I'm going to fix one side using the fixed geometry, and then I'm going to use a roller slider on the opposite side. I could use fixed on both sides, but that would prevent the bridge from collapsing and transfer a lot of the load to the tables. And so unless I'm going to glue this bridge to the tables, that's a bad set of constraints. Whereas fixing it on one side and having it be a slide on the other side will allow it to kind of expand and contract. If I let it be just a roller slider on both sides, it'll try and slide around on the simulation, and we'll get errors from that. So having fixed on one side and then slider on the other side will allow it to move to realistically simulate what's going to happen to the bridge when we test it. And again, those fixtures are both kind of in these options here. And all we're doing is selecting the face we want to apply those fixtures to. Next thing we'll do is we'll add our load. So I'm just going to add a regular force load. I'm going to do this in pounds just because I think in pounds. I don't think very easily in kilograms. I guess I probably could do it in kilograms and be okay. But I'm going to add a 50-pound load to this middle face. And again, that's why I made those faces at the bottom here. So I could have regions to apply the fixtures and the loads to without having it going across the entire body. There is this option up here at the top to do a split. This works exactly the same as the tool we used. And in fact, when you do that, it just loads that tool. So if you know where you want to put your splits to start off with, you can do that. If you want to do it inside the simulation, you can do that too. And those options are there regardless of what type of simulation you're doing in SolidWorks. So, any questions about the loads or the fixtures? All right, the new stuff we're going to add here is a goal and a constraint, as well as the manufacturing controls. So let's start with goals and constraints. Here you have options for best stiffness to weight ratio, right? Maximize or minimize maximum displacement. So if I want to have, can I make this come up a little higher so you guys can see it? Let me just shrink the screen and then pull it up. Nope. Can't pull it up too far. Here. So best stiffness to weight ratio, minimize maximum displacement, or minimize mass. So again, if you're looking for a deflection constraint, which honestly, if you're doing like a bridge design, is probably one of the things you're going to design around, you can use that. If you're just looking for, hey, I just want a good ratio of kind of performance to weight, then that's fine. Most of the time from a mechanical standpoint, you want to minimize mass, right? Like if I'm trying to make this the most efficient design possible, I want to have the lowest possible mass that still satisfies whatever my design criteria are. So I'm going to use that as my goal. They're all reasonably well interchangeable. And you'll notice that even after I select that, I have the same drop-down menu inside the tool as I started with. And that's true for a lot of the things in simulation, where that first menu is really just kind of setting some default options up inside the tool. And again, I have all these constraints I can add. So I can say I want to minimize the mass such that the displacement is less than a certain value. I can say that the mass can't be more or less than a certain range. I can say that the frequency constraint has a certain value. You probably don't want to use this unless you're doing a frequency analysis, but it's the same tool in multiple sets. So unless you're concerned about like harmonics or something like that, I would stay away from that option. And then what we're going to use is this stress factor of safety constraint. So check that. I want to set a stress constraint to a megapascal, and I'm going to say 20 megapascals, which is a factor of safety of 2, because this material has a yield stress of 40 megapascals. So if I can get my design to have a stress of 20 megapascals, then that will still be within my factor of safety. I want to be clear on this. In the design optimization, it tries to make sure it stays, above or below this value. In this one, it actually tries to make it that value. So you're going to get a value inside the stress analysis that's larger than this. But if you're setting it up and it's run with some reasonable accuracy, it should be a lot larger than that. So if you want to be a little more conservative, you might use 15 or 10 on there, so that your factor of safety stays above 2 as opposed to being about 2. Does that make sense? All right, so I'll add that. You can see it adds that to my constraint. If I want to edit that, I can go back and edit it just like you can everything else in SolidWorks, right? So you don't need to add it, redid it, or do whatever you want. The manufacturing constraints here, this allows me to specify, hey, I don't want to lose specific areas of my design. I can say that I don't want a thickness that is less than a certain value. I can also say that, hey, I want to have a draft angle on this, so I can specify a direction for demolding the part. So if you have a part that you're going to injection mold, you can put those constraints inside there. The only thing that I really care about for this is probably preserving the symmetry. I don't want to have a bridge that's asymmetric. So I'm going to do a symmetry plane, and I'm going to define the symmetry plane as the right plane. And make sure that your right plane matches my plane, right plane. It's the middle of the part, kind of cutting it in half. The half symmetry here just means that one half is symmetric with the other half. If you want to have quarter symmetry or 1/8 symmetry, that means you can have like the left and the right be the same. And maybe that would make sense if I did that. So then I could do not the top, the right plane and the front plane. I not double click both these. Oh, I got them separately, right and front. So if you wanted to have more symmetry in your bridge, you can. I don't know how that affects the computational time. From what I've seen, it doesn't make a big difference. You think it would be more computationally easier because it could just do a quarter and then mirror all the results. But from what I've seen, it seems to be about a wash. I'm just going to use the half plane symmetry because that's what I used on the one that I'm already running. I don't want your guys to diverge too far from what I have set up. So use the half plane with the right one. The next thing you need to do is mesh and run this. I really, really, really recommend that you mesh and check the mesh size out before you run. If you just mesh and run using default settings, the chances of you getting a successful output from this is going to be really, really small. Again, if you don't have any idea what your mesh should look like, then go for it and iterate from there. But I really want to mesh and then run. So I'm going to go to the drop-down option next to run this study. Be real careful not to click that run that study because, again, you're going to have to cancel it. It's going to use up a bunch of time. And then below that, you have create mesh. And what I'm going to suggest you guys do is bring your mesh quality down here to somewhere between 1/4 and 1/5 of the way down from the find to the course. And then click on the green check mark. And I'd like you guys to get meshes that have sizes of, this is 1, 2, 3, 4, 5, 6, 7, 8 elements tall. That's probably okay. Something that is this coarse, or maybe even a little bit coarser. So if I do create mesh again, I can rerun this and slide that a little bit further down and then hit it okay again. You can also be a little bit more specific about this, and you can give it like I want a voxel size of this tall. Sometimes that's helpful. If you're much finer than this, it's going to take so long to run this that you guys won't have results by the time we finish the class, and that won't be helpful. Does that make sense? All right. Now that you've got that, go ahead and click run this study. And then while your guys' is running, we're going to try and take a look at the result that I have that's been going since the start of class. Sound good? All right, so let's go back and see if mine finished. Looks like it's still going. The pop-outs are done though, so it's probably very close to being done. It will close. See here, where's my, I should have a way of viewing the study progress. I wanted to leave those pop-outs opened. I'm gonna save and close this part. Maybe I can look for them on the other side. D2, save. Yes. I'm gonna close that part. I'm thinking this is almost done, and that's why the all my pop-outs went away. If you get a pop-up that says allow access, you have to hit no. You don't have admin privileges, so it's not going to turn it. So just hit cancel or no. It should still run anyways.
Okay.
Yeah. I don't know what the advantage of that web add-in is to what that's trying to do. But we don't have admin privileges on these computers, so we can't run those. How do I get my Windows back open? I wanted to show you guys the conversions plots too, so I had left those open.
You have a result.
Oh, did it finish? It still says it's still thinking. Now let's see if we can just plot it out. Yeah, we got results. Okay. So you can see here's the results of my topology study. Your guys's probably won't look like this. And if you can, you should have a little box. Let me just open up the other one and I'll run that so you can see what those boxes look like, and I'll be in the video and everything. And it should have my topology study saved, so I should be able to go to it and just hit run. So when I run this, I didn't want to run it on this one because I thought the other one was still going. Hopefully this will just take 10 or 12 seconds per iteration. Once you have more than one iteration, you can view the convergence data. And the convergence data will kind of show you how on track you are to getting a result out of that simulation. So waiting for it. Where are you at as far as iterations? Jeremy?
Like 20.
20? Giselle, where did you get to? Giselle? Did you finish? Giselle? What? Oh, sorry, Krishana. I'm talking to the wrong person. Krishana, so yours is done. That doesn't look good though. If you look at this convergence graph, it should show you kind of where you're at as far as your mass. I don't know why it won't let me have both these open. It should let me have both of them open. As far as the mass and the target stress. And when the stress kind of gets to that blue line and then bounces around it a couple of times, that's when it finishes. And probably what you'll see in your results, since you have that very coarse mesh, is you may have like a triangle. You may just, Krishana, yours looks just bad. Oh, did it have an error? You may have had an error in yours. Did yours run well, or is it still going?
It's still going on. How did you pull up your graphs?
So yes, the little, it looks like a squiggly line button on here, the little view convergence data and graphs. If you click on that, it's going to give you this pop-up. And then from this pop-up, if you click on the show graph, it'll bring you the graph. I don't know if you cut all of that well. Okay. Jeremy, it looks like you may have had some results that are at least not terrible.
It's like kind of bouncing up and down.
Oh, yours is still running.
Yeah.
Okay. Yeah, I mean, so again, it's lowering the mass on yours, but you can see it still is not going up the stretch yet. So it's not bad, right? If I can lower the mass and keep the stress the same, that's actually good. But again, you're going to get varying results on this, and the coarseness of the mesh that I asked you guys to use is probably too coarse to get good results out. And that's one of the things I wanted to show you. And again, the one that I was running, it ran for about a half hour before it finished. You can finish this early. So what I'm gonna do is I'm gonna stop and save results on this. And it'll show me this simulation. This is kind of what I expected most of you guys to get out of this. And maybe you can tell from this, but this would not work as a design, right? It's saying that I could have a hole in the side of this part and have it still function for supporting a load, which is obviously not true, right? And the problem with this is when the stress distributions are too small, basically the variance in stress isn't sufficiently large, it basically gets rid of everything. So the video I have that I'll post on Canvas from this morning is I did an axial load. And then if you look at the results, it says you can have the 2 plates with nothing in the middle, right? Which is obviously wrong, right? But because there's no variance, it doesn't know where to take the material away, right? So since it doesn't know where to take the material away, it just says, I'll just take the material from everything equally and it'll be fine, right? And so that's why you need to have variance and stress and a high resolution, because that'll allow for localization of stress concentration, which will give you results. So hopefully that makes some sense here. Inside this, I'm going to go over to my better model so we can see how these sliders kind of work out and give us some different results. In here, you can see that this one actually gave me a pretty good result. You can actually see that I almost have a truss, right, inside the system. And I've got this top plate, which is distributing the load, because again, since I'm distributing that load across the entire top plate, I have to have something there. And the same thing on the fixture is keeping those fixtures in place because the load is being distributed across those bottom pieces. And then I can go into this a little bit more detail by double clicking it. Oh, I don't want the name, I want the icon. There we go. And I can change this slider to make it lighter or heavier. You got to be a little careful about how far you go on that. And that basically just bulks up or debulks around the solution. And the must keep are the ones that are kind of within the stress values that it said. And the ones that are below that are lower than that by some factor. But again, because I don't have, once I get smaller than my element size, it no longer has any meaning, right? So even though, at this configuration, the stress on these blue areas is less than my 20 megapascals, I still need to keep them because once I delete that element, I no longer have anything there, right? So it says, yeah, you get a factor of safety of like 5 here. But then when you do it one step down, you have a factor of safety of 0 because you have nothing left, right? And the more kind of refined your mesh is, the more you'll be able to kind of use this slider to add material and take it out without getting something that's obviously not going to work, right? The other thing you do here, that these are always end up being bumpy because, again, you're just removing voxels from the mesh. So you can smooth these out. The smoothing oftentimes can have the same problem where, hey, you've made something that no longer works because you've thinned it out so much from that bumpy shape. You can adjust the sliders here to make it, a little bit of a compromise between the smoothness and still having completed geometry. And you can also bulk this out from the results and then smooth it on here to get something that's a little bit better, right? And again, there's not like a hard, fast rule of, hey, if I lower this out to the max and then I lower this to the max, I'm going to get a better result. You kind of have to play with the different pieces here and then use some intuitive judgment as to what's going to work well. So if I was going to print this out, I'd probably go with something like this, right? I've got reasonably strong pieces that I can go and print. And then I also have, no gaps in my results. Once you've got that kind of set up the way you want it, if you click the check mark, you can then export this mesh into another part. So you guys can follow along with this on yours, even if you're not going to use it, or you can just watch me go through it. I'm going to right click on this mesh, and then I'm going to export smooth mesh. It's going to say, what do you want to do it to? I can do it to a new configuration. I can apply it to the active configuration, which is basically going to replace my part. I would really recommend you do this as a new part. And then you have options for where do you want to save that part to. I'm going to try and move this over so you guys can see it a little better. So here is the part file. Again, I can name it whatever I want. I'm just going to call it bridge to body because I don't like names that are super long. I also have options here for my sets. I would really almost always recommend you export this as a solid body. because then you're gonna be able to use that result for a lot more options. If you really want it to be a graphics or a surface, that's really only gonna be valuable for you if you're trying to use that for rendering purposes, right? So if you don't plan on printing this or using this for doing any kind of model refinement, then those other options are fine. But really, you probably want to use that solid body option. And then I can always browse to put this wherever I want to. I'm going to go just put it on the desktop. And I'm going to save it. And it's kind of annoying. It doesn't give you the option to export straight to STL. But once I have that as a part, I can open up that part. I'm not going to do feature recognition. And you see, I already have this mesh result. If I wanted to rerun this in another study, I could, right? And I could say, okay, well, what is the stress concentrations in this current part? I can also just come in here into File, Save As, and then I can change this to an STL. And now I've got something that I can use to 3D print that result. And so maybe we'll compare that one to the results that you guys build from your projects. Let's compare this. I'm going to set the material on this result to my polycarbonate ABS, which looks kind of funky. And if I evaluate the mass properties, this has a mass of 0.194 pounds, so about 1/5 of a pound. And what I want to do is I want to compare the results of this to a parametric study. Sound good? All right. So let's make a very simple model of a bridge. And I'm going to model it based off the results that I expect you guys to get, where it's basically just a triangle, right? With a bridge at the bottom. Let's go into new part. Okay. I'm going to make a base plate, and then I'm going to make 2 triangular supports that kind of come up. And actually, I can probably do that in one feature and then shell it out. Yeah, let's try that. So let's go to the front plane. I'm going to sketch on the front plane. No, it's not giving me sketch options for the front plane. I'm going to close this topology study results. Maybe that's the problem. There we go. Sketch on the front plane. I'm going to start with my center point rectangle, and then I'm going to cut it out. So we'll do 2 inches by 10 inches. And then I'm going to basically make this into a triangle by adding a line that cuts across the corner. I'm on the front plane. Oh, I didn't mean to exit the sketch. And then I'm going to align this left side with this right side. I'm going to make that horizontal. And then I'm going to add some smart dimensions here to specify that I want this gap at the top to be the same basic setup as I had before. So I'm going to do 0.25 to the left. I'm going to do it 0.5 across the top. Then I guess for consistency, I'll go ahead and make this top portion 0.25. And this left portion, I have those constrained already. So I don't need to do that left portion. And then I'm going to trim off the top pieces. Oh darn! I lost my dimension. I'm going to add my dimensions back in. And I lost my constraint on that too. I'll use the midpoint of this bottom line and my origin. I'm just gonna make this coincident. Oh, that didn't work. I'll make them vertical. I need to set the total height of this to my 2 inches again. Did I not get the relation there? Oh, I got that one. I guess I'll set this up so it's 5 from the bottom. Or not 5, 1, half of the 2. Using the center point rectangle didn't actually save me any time there, but it has the same kind of general center as my previous model. So that's a little bit beneficial from a comparison standpoint. And then I'm just going to use this to do a thin extrude. So let's do features. And I'm going to do a extrude boss base, thin feature. And I want this to be the inside, so I'm going to flip the directions. That way my outside is basically the parameter that I have across from there. And yeah, let's start with 0.1 inches. That's probably okay. I want to check and see how much I can vary this and still have it work. So it'll work all the way up to about 1 inch thick. And I can go as thin as I want. So, but I'm going to start with 0.1. And I'm going to extrude this out. Oh, wait. I didn't specify the direction. I want this to be a midplane of 2 inches. Right. And I'm going to add my polycarbonate to this as well. And I'm going to delete the appearance because I kind of hate it being clear. So this one here, just to start off with, is already lighter than my previous one, but I don't know if this is going to be a successful design or not. So what I'm gonna do is I'm gonna set up a design study and then I'm gonna make the dimensions of this the parameters of the design study. So let's go into our simulation. We're gonna do a new study. And then you can see the design insight. We're just going to toggle from topology to design. Yeah. I use 0.1 for the thickness. Yeah. And it's 2 inches wide. Yeah. And actually, before I do that, well, I guess I can do it inside the design study. I need to split this bottom line. Yeah, let's do it from the study so you guys can see that. So we'll do a new study, design study. Okay. We need a simulation that we can run this off of setup. So I'm also going to go do a new study. And then we'll do static. I don't know why it keeps applying my appearance when I go into the simulation. I think it's because the material for the simulation is inherited from the part. And so when it does that, it also inherits the visual properties. So we'll use the same thing. I'm going to use a fixed load at the bottom on the corner. Oh, I don't want the advisor. I just want the fixed geometry. Again, I'm going to go to the split option. It re-added that visual property again. Stop adding the visual appearance. No, it's not even there. I need the sketch for that still. So I'm going to sketch the lines. Set those as a 1/2 inch from the side. Again, the same setup as I had before. I don't need to do it for the top because the top is already set up that way. And then I'll go back into my fixed geometry, split. There's the sketch. And then the face, I'll click the bottom face. Then I want to create, oh, yes, I want to create the split. Now I can go back and I can add my loads to this. Yeah, it's still 0.5 inches. I don't like the way it's visualizing that. It should only show it on one face. Again, I want to make sure I'm only fixing one side with the full fixture. I'm going to use the roller slider on the other side. You can see here that it actually created the split line for me inside the model when I did that. I would probably recommend that you do the the split first, just because I think that's a little bit easier to set up than it is to do it inside the simulation tool. And then I'm gonna add that 50-pound force to the top face here. And I want to run this. Keep in mind, this is a deformed scale, so it's not actually going to look like that when it's done. We're getting a stress concentration here in the corner, but my maximum stress is looks like 100 megapascals. No, 10 megapascals. So this is still going to have a factor of safety of like 4, right? And again, we were already lighter than our original design, right? And this stress concentration in the corner, I could probably fix pretty easily just by widening out just that one piece. Yeah, Jerry.
What is your load on this one?
I use 50 pounds. At least I intended to use 50 pounds. Yeah, 50-pound bars. Since I know that I don't want that corner to really extend that, and I don't really like the fact that this is bulging out this way, what I'm going to do is I'm actually going to fill in the center portion of it, so that way it distributes the force a little bit more evenly across the bottom. So I'm going to go back to my model. I'm going to go to the front plane. I'm going to sketch there. I'm going to convert this middle piece. And then I'm going to extrude that out. Again, as a mid plane, I'm going to make it 0.1 inches. And that's going to create like a rib down the middle of my part. And then I'm going to rerun my static study to see if I can get rid of that localized stress concentration. That was kind of my megamo thing here. All right, so that's pretty good. I've got a distribution of stresses. I'm going to use this as a starting point for my topology study. Again, here we got a factor of safety that's very, very high, right? So we got 6 megapascals is our maximum stress, and our goal is 20. So I'm gonna go to my design study, and I wanna try and optimize a few different variables here. So I'm gonna go to add parameter under variables. Yeah, well, it was 0.1. Yeah, same as the thickness of my part there. So my variables, I wanna add parameters to here. When I open up this add parameter option, I get all the different dimensions inside my sketch. So I'm going to use this thickness of my mid portion. Let's just call this thickness, I guess. And then I'm going to say I think this right here, this is my thickness of my part. That was my thick. I think I accidentally replaced my first one with thick. Be careful where you're selecting on these. Select the one you want to change and then click it. I probably shouldn't have made them the same value because it's hard to tell which one's which. This is the web. I call that the web. And then every time I hit apply, it gives me the option to click on a new one. Unless I break Solidworks. Come on, Solidworks. I probably should have closed all of my other parts before I started doing this one. Would have been smart. Because now I have 3 topology results sitting in my background. I'm going to do that now. So I'm going to close these ones, save all. I don't remember which ones are which. There we go. That's going to be better. Where's my variable box? I got to bring that back up. All right, so those are my parameters. I also want to do the total thickness of this. So I'm going to go to this third option. I'm going to call that the width. Now you can optimize all of these at the same time, or you can do them one at a time. Optimizing them all at the same time, obviously, is going to take a lot more iterations than trying to do them one at a time. In fact, the design study on the student version, the Design Express, will only let you do one at a time, which is not a terrible thing. But again, we have the options here. One thing you want to keep in mind, I already know that my factor of safety is higher than it needs to be. So set your balance to something that's reasonable. If I already know that 2 is thick enough, I'll set the max to 2 and the min to 1, right? Kind of the same thing here. If I know that my webs are already thick enough, I might want to set the maximum to a smaller size, say 0.1, right? And set my minimum to maybe 0.025 or something, right? Don't go crazy with these. I would generally suggest not doing something that's smaller than a quarter of whatever your current size is, and then set the maximums based off of whatever your initial stress results were. So you might want to go somewhere between a quarter down to 4 times of what your size is in any given set. Also pay attention to the step resolution here. That's going to determine how many different types of iterations you have to run, right? So I have 18 scenarios. This is going to run 18 times before it is able to converge on any kind of results, right? So if this number is 1,000, it's going to run at least 1,000 times. Does that make sense? So to run all of these configurations, it's got to run at least 18 times. The constraints, again, I want to minimize mass. So I'm going to add a sensor. I'm just going to say mass. And my goal is to minimize that. So mass is, I want to do my sensors for, I actually want to add a stress sensor, and then my goal is the mass. So simulation data, this is why I had to run the simulation first. The stress von Mises stress in megapascals across the max in the model across all steps is what I'm looking for. And let's see if I can get rid of this one. Delete that constraint. And I want to say it's less than 20 newtons per millimeter or megapascals. And again, I'm using the static 1 setup. Again, that's why you have to have the simulation set up before you come into this, at least if you want to use that simulation as your constraint. And then my goal is minimize the mass. And now I can run this. And again, this is going to take a while to run. So I don't know if it's worth it for us to stick around for all the results on this. But it's going to run all the scenarios, test all those different thicknesses, and then it's going to tell me which one of those were successful. They basically had a maximum stress, which was less than whatever the value I specified, or a maximum stress more than the value I specified. It looks like it's doing the smallest scenarios first and working its way up. It's 7 of 20. I know you guys have class in 7 minutes. So if you want to stick around and see what this looks like when it's done, feel free. If not, then that's okay too. I'm going to record it so you can always go back and you can watch the recording to see what the result was. Halfway there. The nice thing about this, it should also tell me what the stress was at each of these steps. And so you get a pretty good idea of, what works better or worse by the time it's done. I hope I typed in all of these correctly. So at least some of these should work. It says that my optimal was using a thickness on that border of 0.1, which was my default. My width was 1 inch, so half of the original width. The web 0.25, which was the minimum value that I had. So maybe I didn't really need that web at all. And that gave me a stress of 18 megapascals, which is just a little bit less than my target value, right? I can scroll through all those and see which ones were successful. Basically, the gray ones are the ones that were successful. And I can, ones that were unsuccessful, I can see kind of by how much, right? So this one here was only 22 megapascals, which is not failing by that much, right? And then I should be able to apply the results to the model. If I just click on this optimal 3, that's what that optimal looks like. And if I do the mass properties, let me say this is down to 0.09 pounds, which is about half of what we got from the non-parametric study, right? And also, not quite half of what we set up originally. To be clear, this is not an idealized bridge design, right? It's a fairly simple bridge design. But again, would not also be super difficult to manufacture this, right? So you can consider those different things too. Yeah. For the, the constraint is the stress less than 20. And inside this stress constraint, I can edit this, right? I'll just add a new one and then remove that one. There's a lot of different options here. Most of the time, the defaults are what you want. So stress in megapascals across the entire model, across all steps, right? You can change this to do a specific plot step point or transient. Most of the time you want just if you're looking for this stress, you want the maximum stress in the entire model, right? But if you're using like factor of safety or something like that, then you might want to change some of those options a little bit. Or if you want to ignore certain regions of the model, you can do stuff like that too. All right. Thanks for coming, everybody. If you have questions, let me know. If you are working on project 2 and you're ready to print, then send me those models. And I'll see you all next week. Hopefully.